Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Not long ago, I was visiting a ham radio swap meet. I was walking around and I spotted this really neat looking old transmitter on a table. I figured, hey, that would make a really neat video to share with you guys. So I bought the transmitter. I talked to the fellow that owned the transmitter for a while, and it turns out that he watches this channel. He had a whole bunch of neat things for sale on his table. So I purchased the transmitter, and today we're going to go through this transmitter and make it transmit again. So let's get started. This is a 1950s era Globe Scout Model 40A transmitter. So there is no receiver in this. All this thing does is transmit. Way back when, you were expected to have a separate receiver, and on the back of this thing is a bunch of terminals that allows you to connect this thing to a coaxial switch, which will switch between the receive and transmit when you click this up and down. So when you click it into transmit mode, it basically opens the coax to the receiver and just allows a path for this to go out your antenna. When you click it back to standby again, it disconnects this and connects the receiver back up to the antenna. So this was all separate from this unit here. This is an AM and CW transmitter. This doesn't do sideband or FM or anything like that. It's just very basic AM and CW, and AM is a very enjoyable mode to chat in. To operate something like this, you need a crystal or a VFO. So VFO stands for Variable Frequency Oscillator. So what that'll allow you to do is move around each one of the bands. You can see that this is a band selection switch here for 160, 80, 40, 20, 15, and 10. So basically, if you wanted to move all around the 80 meter band, you would attach a VFO to this and you can move the VFO around, and basically it's going to move your transmit frequency around. So that is a little bit more desirable in some cases than in having a crystal in the front of it, because whatever frequency you want to talk on, you have to have a crystal for it. So I'm going to look through my box of rocks here in a little bit and see if I can find a crystal for this thing, and see if we can fire it up on some band. I've got a whole bunch of crystals, so find something for some band here, and we'll see if this thing puts out any power and if it's even working here in a little bit. What we're going to do is open this thing up and first of all see what kind of condition it's in and go from there. If it's all original and all that kind of stuff, what we're going to end up doing is, doing some recapping inside of it and, making the thing safe to operate. I don't know what's inside this thing. I haven't opened it up yet, so it could be all original, or this thing could be filled with rocks for all I know. I really don't know. So this is where you attach the microphone. So this says filament and gain. So filament is, if you were to have this in the off position, basically the Globe Scout is just off. When you click this like this, now it's on. So basically the filaments inside are energized. So what's happening in there is basically all the tubes are just lighting up. Now when you click the transmit switch, this of course is going to apply plate voltage to the final tube and to that area there. And of course, we're going to have some transmit happening here. So that's the difference when you see filament and plate. So the red light usually means that high voltage is energizing on more tubes inside. So now, depending on how this is wired, I haven't looked at the schematics for this thing yet. Sometimes some of the tubes do have high voltage on them all the time, or in some cases, when you click the transmit switch from standby to transmit, it just energizes everything with high voltage. So what I'll do is I'll dig up a schematic here in a little bit, and we'll take a look at that schematic, figure out what they're doing in here. This is the phone and CW switch. So phone is basically AM, so you can hook a microphone to it and talk through this thing. I don't know what the modulation scheme is inside this thing. We'll also take a look at that. CW means that you're going to hook a key up to this thing and you're going to be sending Morse code with this. This is the oscillator tune, so the oscillator would be attached to this section here. So if we're going to stick a crystal in here, we need to tune the oscillator, and we're going to be looking for that on the final grid. Now, I don't see if, yeah, that is present in the camera, so final grid here. So this is for the final amplifier, and this says final plate. And then once we have grid current, then what we're going to do is tune it up and see how many watts we can get out of the Model 40A. On the back side of the transmitter, we have quite a few connections, and some of these connections are extremely dangerous. And I'll tell you about those connections here in just a moment. We'll start with this side first. So this connection right here is just for the radio station grounding system. So you can ground this to all your other radios and safely ground the case of the transmitter. Here we have two SO239 connectors. So this is marked antenna, and on the top here it says doublet. So since we're going to be testing this thing into a 50 ohm system here in a little bit, and we'll see how many watts this makes, and we'll see if it even modulates, we'll be using this jack right here that's just marked antenna. Chances are I'll be using that Marconi 2955 back there to do that. This here is the antenna relay connections here. Now, here's the thing with most of these older transmitters. If you recall that switch on the front that went from standby to transmit, well, when you click it into transmit, it takes the AC from the line cord and puts it directly on these two jacks right here. So, for example, if you were to reach around the back side of this thing while this was plugged in, you would be in for a very nasty shock. And that's just how things were back in the day. You were expected to know that when you owned this transmitter. This was built back in the 50s, an era where people took responsibility for their own actions. And that's how they built things. Most of all of these, really, these older style transmitters had some form of high voltage or something exposed on the back. Even the Johnson radios, they had a crystal socket on the back, which is, normally for plugging crystals in, but they used that crystal socket for the same idea. If that's not bad enough, this jack here is usually known as an accessory jack, and most of the time they bridge the filament and the high voltage in this plug here. So this should come out. So there you go, basically like an 807 type pinout right here. It's like basically what this is an 807 socket. So that's usually what happened here. Now, I'd be very surprised in this thing if this was some form of low voltage. They're usually full B+. So whatever the high voltage is in this thing, that's usually what is in these sockets. Now, some of the times, these sockets had a little cup on the back side here that would protect this so that you couldn't touch this. But a lot of the times, they were just left exposed like this as well. So line AC right here, full rectified B+ right here. Very, very scary. This really, really hurts if you come across this. That's all I've got to say. Now, the B+ inside these, or the high voltage, I should say, it's called B+ in these older things, all right? So the high voltage in these older transmitters has a lot of current behind it because it has to power a transmitter. So when you're working on an older radio receiver, they have high voltage in them as well, but usually at a much lower current. This thing is really heavy, and I'm imagining it has a pretty large transformer inside this. So again, I haven't opened this thing up. We're going to take a look inside this thing. It is very, very heavy. And what I'm going to do is dig up a schematic for this thing as well, and we'll take a look at the schematic, and we'll see if this is all wired like this. As I say, most of the time it is. I'd be very surprised if it's any different. So I've worked on so much of this older stuff, it's all the same. Line cord fuse here, and the line cord itself, which looks to be in very decent condition. So not a problem there. And that's what this all is on the back. Now, this looks like somebody's added this, some form of an RCA connection here. I do not know what this is or where this goes or anything about this. So we'll have to find out. This could be attached to this, or actually I don't think it would, because these are isolated from the chassis and this is connected to the chassis. So this is going to be some form of an input, maybe VFO or something like that. I really don't know at this point. So we'll check this out when we take a look inside and see what this thing is connected to. Now, I noticed that there's two holes drilled on the back. This is very common because this is where people would normally attach the relay that would switch the coaxes. They would just attach it directly to the back of the case. And chances are that's what these two holes were for. So it probably was on an angle here so they could get the coaxes down here and things like that. Now, that relay is long since gone. And I don't think I have one of those kicking around here. I usually use an electronic form of switching, and I'll go over that here in the future as well. In fact, chances are together we're going to end up designing a bunch of things together here. We'll design an electronic switch for older transmitters and things like that as well. So what I'm going to do now is get this thing turned around again, and I'm going to remove this from the case. So I'll take the case off of this, and we'll take a look inside and see what we're up against. Hopefully it's in nice condition. Getting the transmitter out of its case was very easy. I just removed all the screws on the case, and this whole thing just slid right forward. It was just that easy. Everything is marked on the chassis here. All the vacuum tubes are marked, so it makes this thing really easy to figure out. We know that this section here is the audio chain. So we can see we have two audio preamplifier tubes. And this is a 6L6 here, a metal 6L6. We have a power transformer, really big power transformer. So this is making up the bulk of the weight, these included. So we have this power transformer here. We have two filter capacitors. We have a rectifier tube, so we know that we're going to have our high voltage in this section. We have our final tube, which is the 6146, and this is a 6V6 over here. I'm imagining that this is most likely going to be the crystal oscillator tube right here. So a 6V6 vacuum tube in modern equipment, like a guitar amplifier, they're used for audio. The 6V6 is still a very, very common tube, as well as the 6L6. This is just the metal version of that 6L6. Now, where these things differ from radio receivers is, in radio receivers, usually when you see a cap on the top of a vacuum tube, that cap is usually where the signal goes in. So there's usually no B+ present. Now I say usually. In a transmitter, when you see a vacuum tube like this is where the RF is coming out of. So there's full B+ or full high voltage on this right here, and this is all high voltage stuff right in here. Sometimes they place high voltage across the meters, and the pilot lamps have high voltage on them. These things are full of high voltage, and it's exposed everywhere. So if you're ever to work on one of these things, keep that in mind. If you're unfamiliar with working on something like this, do not do it. If you get a shock from one of these things, it can be lethal. Very, very painful at the least. You got to be very, very careful. So that's the rundown of the top side here. Let's take a look at the bottom side and see what that looks like. Well, surprise, surprise. Somebody's been in here and replaced all the electrolytic capacitors, and they did a really good job too. All the new electrolytic capacitors are put on this perf board here. None of them are touching. They have lead-out wires that run to where they're supposed to tie into. The perf board is stood off the chassis with some standoffs. That is a really nice job. Now, I've worked on a lot of these older transmitters, and usually the jobs that I find in, on the underside of the chassis are really bad. Let's just put it that way. This looks really, really nice. So the fellow that I met at the swap meet, if you're watching this and you did this job, you did a great job. That looks really, really nice. Nice and clean. So this thing is pretty much ready to apply AC to the line cord here and see how many watts this thing makes. See if it modulates and all that stuff as well. So we'll take a look at some of the components on the underside here just before we go about taking a look at the schematic and firing this thing up. So for those of you that aren't familiar with point-to-point wiring, this is what point-to-point wiring is. These things here are an early form of IC. So you can see that they've got 4 lead-out wires. This one has 4, and this one here looks like it has 6 lead-out wires. And there's a whole bunch of resistors and capacitors inside this little block here, and that's what they did to make things smaller back in the 50s. So you can see that they were already starting with a basic type of IC in these units right here. So there's 2 of them in here. Basically resistor and capacitor combinations in these little cards that you see here. And unlike what they do nowadays, on the schematics, they told you exactly what was inside these in most cases. They didn't just put the numbers on, they showed what was inside them. So 2 early forms of ICs here. We can see the audio jack on the front here. This is the wire runs into this tube, so we can see that this is definitely the audio chain. A bunch of large resistors here, some chokes, all ceramic disc style capacitors. There are no paper capacitors, so there's really nothing to worry about in this thing. And it looks like this piece of coax from the back side here, where that RCA jack is just running directly up to the front crystal jack. So yeah, they're just using this as an external VFO input. Very, very clean, nice construction. So let's take a look at the schematic, see what their idea was when they put this thing together, and then let's plug the thing in and see if we can get any power out of it. Let's tune it up. Here's a pretty decent schematic for this transmitter. Somebody's written on it, but it's still very understandable. I like the design of this transmitter. It's really nice and simple. So let's start here where the microphone attaches to the first microphone amplifier here. So this is the microphone jack on the front. The audio signal will go directly into the control grid from the microphone. This is a pentode, so we're going to get quite a bit of gain in this tube, and our amplified signal is going to be present on the plate here. The plate attaches directly to one of those little cards that we looked at on the bottom side of the chassis, or one of those early type of ICs, if you'd like to call it that. And as you can see, they've drawn the resistor and capacitor combinations on the inside, which is really nice as well. So again, the audio signal path in the control grid, it gets amplified signal on the plate. That signal travels through this capacitor here down into this variable resistor, which is on the face. That is the mic gain control. The wiper of the variable resistor, so the wiper is the part that moves along the carbon path, runs directly to the control grid of this 6C5 triode. So the signal gets amplified again, it's present on the plate, goes down this path here into another one of those cards or those early ICs, through this capacitor down here and into the control grid of the 6L6. So this is the modulator tube here. So you can see the plate of the 6L6 ties directly to the plate of the 6146, giving our mixing action. As you can see, the B plus line here goes through that plug on the back, so it does go through there. High voltage comes out here to here, jumps to this side here, goes down here, through this modulation reactor. So this is a form of Heising modulation right here. Goes through the modulation reactor here, and then of course we get our B plus or our high voltage on both plates, and we get our mixing action. So this is creating RF, and this is creating audio down here, or amplifying the audio that's being created by you and being spoken into the microphone. This is our oscillator tube here. This oscillator tube is basically controlled by a crystal, or if you wanted to, you could plug in a VFO into this point right here. So whatever frequency the crystal is, this is going to oscillate. And then we have a coil here, which basically tunes to our proper band. These two are ganged together. Now, in a lot of these schematics, they don't tell you what end is which, and there's a very easy way to figure this out. The further you get away from the plate of the final tube, the lower the frequency, so because there's more coil in there. So this would be the 10 meter, 15, 20, 40, 80, and 160 meter taps as you go along here. And it's the same for this here as well. So as you're moving this along here, as you get closer to the plate, so you can see here we're closer to the plate side here, this is going to move down like this. And as you can see, the arrow is drawn at the same position, so it shows you that they're both at that end at the same time. When I say gang together, that means that when you turn one shaft, both of these move at the same time. So these two are ganged together. This is known as a pi network. One very easy way to remember a pi network is you have a coil in the middle and you have two capacitors. You can see that the both bottom ends of these variable capacitors are tied together and to ground. So if you were to take the bottom of this capacitor and tie it to this bottom and put a ground here, you would have a pi-shaped symbol. Very easy way of remembering a pi network. That's what that is. This is a parasitic trap on the top here. Parasitic suppressor, they have P dot S dot, so parasitic suppression. That's that coil around the resistor at the top side of the 6146. The reason that they have that there, so you have the coil and the resistor, is basically so this tube here doesn't turn into its own oscillator. We don't want that to happen, so this stops any type of parasitics from forming parasitic oscillations. See, what else can I tell you here? Oh yeah, remember how I told you that there's AC on that relay jack? Well, it turns out there actually is. So it's pretty common with all of these transmitters. So this is the plug, and as you can see, we have a switch. So this is going to connect across here. So as you can see, we have a path here, down here, through the standby and transmit switch. This is going to connect to here, runs up to here, over to here, and directly to our jack on the back. Somebody's written 47 on the bulb here. That is incorrect. This is not a 47 type bulb. A 47 bulb is a low voltage type bulb. If you did put a 47 there, it would just flash very brightly. So this would be the 47 up here, if anything, and then this would be just a standard, 120 volt style bulb, like a Christmas light bulb in here. So we can take a look at that here again when we start tuning this stuff up. So the standby and transmit switch is basically a double pole switch here. So single pole, or double pole, single throw, I should say. So you can see here the center tap of this transformer runs down to this switch here. And you can see that it's when you move the switch down to the transmit, these two arrows are going to connect. So this arrow will connect here, this arrow will connect here. The center tap of the high voltage winding will be attached to ground. So that's what they're doing to cut the high voltage. They're just breaking the center tap. This is known as a full wave rectifier here. You can see both ends of the winding are attached to the plates. So we're going to get full wave rectification. Since this is a directly heated vacuum tube, it has its own filament winding. The filament windings are attached directly to the filaments here because there is full DC on here. So the B plus is present on this. So we have the AC from the filament winding lighting the filaments, and we also have DC present because of the rectification happening in the tube. So we have filters over here. So we have two capacitors here that are in series. So they're doing that just to up the voltage. Of course, the capacitance drops in half and the voltage doubles when you have that. And then we have a filter choke right here and another two capacitors in series. And we have a bleeder resistor across that, just in case you pull this plug out. So if you pulled this plug out here, these capacitors would stay charged because there's no path for them to bleed off. So that would be a bleeder right there. And then our high voltage goes through a jumper in this plug and over to this side, and it feeds the plates and the screen grids of the tubes over here. The two larger pins are the filament connections. You can see the filament is tied to ground. The pilot light is across the filament. There's going to be a jumper from the large circle to the large circle here, and we're going to have filament power for all of the vacuum tubes. So it's going to light up all of these filaments. The filaments are the little arrows under the cathode here. So what else can I tell you here about this? So we have high voltage on that plug on the back. We have full AC on that relay jack. There's high voltage everywhere in these things and on the outside as well. So if you ever work on anything like this, definitely study up on this. Be very, very careful. And again, if you're unsure of working on stuff like this, definitely don't do it. There is a lot of current present here. So we definitely don't want to have anything bad happen. Be very, very careful. Let's see, what else can I tell you about this? I think that's pretty much it for now. Oh, this is K1 is the CW jack. So you would plug the CW or your key in there, and it basically breaks the cathode connection of this oscillator. So that's for the Morse code key gets plugged in. Pretty sure this crystal circuit would draw a little bit of current. Probably going to warm up some crystals on this thing. It says 6F6 here. I'm pretty sure that this here is an addendum. This is probably an earlier version because in this, on the chassis, it's clearly marked 6V6. So they've probably made some changes over time. Phone and CW switch here. So these arrows are basically going to move down like this. So just depending on what position you have this in. These here are meter shunts. So we have a meter shunt here for the plate. So the B plus here is present on this line. So if we want to measure the plate current of the 6146 here, we need a shunt. And you can see C and D is written here. And if we look down here, we see C and D, and this is the meter on the face here. So this would be to monitor the plate current. Now we can also monitor the grid current, so there's going to be a grid shunt on here as well somewhere. So the grid of the 6146, and there's the grid shunt right there. So we see A and B right there, so this would be A and B. And it says grid right there, so there we go. So grid and plate. So this is going to give us the ability to look at the grid current, and this is going to give us the ability to look at the plate current, and that's that switch on the face, and that's basically how we tune this thing up. And I'll show you exactly how that's done here in a little bit. And I think that's pretty much all. The RF output or antenna output jack from the Globe Scout is attached to the input of my Marconi 2955B analyzer through this piece of coax here. So we can monitor the RF output power and the modulation here in just a little bit. I have the line cord for the Globe Scout attached to my isolation transformer and variac supply, which is fused and current limited, so the Globe Scout is really protected. Before I go about turning on the filament switch here, I want to make sure that a bunch of switches and knobs are in the right position or very close to a very good start position, let's put it that way. I also want to make sure that the final tube has some form of drive. So I'm going to either plug in a crystal or I'm going to use a VFO for this. Now I've looked through my box of rocks and I found a crystal that may work, so we'll try that first, and if this works we'll just stick with the crystal. The crystal has 3640 carved into it, so chances are some ham radio operator has moved this crystal around. I don't know if you can see that right at the top there. It says 3640 above my finger. You may or may not be able to see that. At any rate, we'll plug that into the crystal jack. That puts this into the 80 meter band. The very first thing I'm going to do is put this onto the 80 meter band. Now before I turn on the AC power or the filaments, I want to make sure that the transmit and standby switch is in the standby position. I want to make sure that the phone and CW switch is in the CW position. I'll start with the oscillator tune at 12 o'clock. I'll start with the final plate tune at 12 o'clock and the antenna load at 12 o'clock as well. I also want to be monitoring the final grid current. That'll help us tune the oscillator here. So what I'm going to do now is turn on the filament switch and let the vacuum tubes warm up. I think you can see the filaments glowing in that tube in the back there. That's the rectifier tube. That's a directly heated vacuum tube, so that one will come into emission first. The other tubes will take about 10 to 20 seconds or so. So hopefully this thing comes to life. We'll see what happens. Bunch of things at play here. Hopefully the crystal works as well, so we'll find out in just a moment. Alright, so that should be about warm enough. So what I'm going to do now is click this into the transmit position, and I'm going to tune the oscillator tune for maximum current here. So I'm going to turn this until I see maximum current on the meter. So here we go, into transmit. I'll move this around, and there we go. So if I pass it, I'll back up, and right there is maximum current. So far it's looking really good. Now what I want to do is monitor the plate current, and I want to tune for a dip with a final plate tune here. And when I do that, we should get some substantial output power if the 6146 is working right, and the 6V6 is working right, and the crystal and all that kind of stuff is all working right. So here we go. It's in transmit now, lots of current. I want to tune for a dip, so I want to bring this down to the lowest position. And there's the dip, and I'm already making just about 11 watts of output power just by doing that already. Now you'll find that bringing the final plate tune out of the dip a lot of the times will give you more RF output power, but you have to be going the right way. If you go the wrong way, you'll bring the power down. It'll come out of the dip, but the power will be going down. So you have to be tuning the final tuning capacitor in the correct direction. And with skill and time, you kind of get used to doing all of this stuff when you're working with these old transmitters. So I'll just show you on the analyzer here that we are getting some decent output power. So there's 10.9 watts. So what I'll do is I'll bring this out of the dip in one direction, and you can see it's going down. So the plate current is rising. So what I'll do is I'll just dip that again. Right there is the dip. So that's the dip where we were at. You can see when I was going in the other direction, it was raising. So no matter what way I tune this, unless you have an RF power meter, this is really hard to... So you'll see that if I tune this control this way, you'll see that it comes out of the dip. Now if I tune it the other way, you'll see that it'll come down to the dip and rise again. You see that? So any way I tune this, it's going to come out of the dip, but if you go in the wrong direction, you'll actually detune the power to a point to where you'll damage the final. So that's very important to watch. So a really safe way to load these things up really is just to use a watt meter. But again, bringing it into the dip is always safe. So I'll zoom in on the screen here. So you can watch the wattage move up here, or you can watch it here if you want. This is modulation. We're not doing that test yet. So in order to bring this up in the right direction with this particular tune, it seems that I'm going to go clockwise. And you can see that when I go clockwise, we get about almost 21 watts out of this. And if I move the other control and move this around a little bit, we get about 21 watts or something like that. And it looks like it's just below 150 milliamps. And that's out of the dip again. So this could be, tuned down towards the dip, and, you can reduce the wattage if needed. So yet to see if we're going to get any type of modulation happening at that level. So you might have to actually turn the power down just a little bit in order to, achieve 100% modulation with this particular transmitter. That's yet to be found out. So what I'm going to do is I'm going to click this into standby again, so you'll see the power drop off. So there's no high voltage flowing. And what I'm going to do is flip the switch from CW to phone, and there should be a little bit of a reduction in RF output power. So click this back on. Not too bad. And I'll click that off again, click that back to CW. And as you can see, it's up just a little bit, coming up to about 20 watts. As things are kind of warming up from drawing current. I have an audio signal generator attached to the microphone input jack, and I have the mic gain turned up just a little bit, so I'll use the gain on the signal generator itself to turn this up. So what I'll do is I'll click this into transmit mode, and we'll take a look at the analyzer here. So I'll see how much modulation I can get out of this thing with it set to this wattage here. So here we go. You can see the level right under the mod freak going up. Just a random frequency I chose with the generator. And it goes to about 70%, and it's topping out there, and I'm pretty sure it's not a clean sine there at all. So what I'll do is I'll just leave this up around 70%, and what I'll do is I'll bring the plate more towards the dip so that it's drawing less current. Of course, the wattage is going to drop down, and we should see a rise in the modulation level. So as you can see, yeah, it's starting to rise quite a bit. So it's actually, it went over 100 there really fast, and that's why it's popping into another range. So I'll just turn this down. Turn that back up. You can see it's heading right towards the 100%, no problems there. I'll just turn that off. So with the wattage, no modulation or anything happening here. So you can see the wattage is at about 11.1 watts in order for us to achieve close to 100% modulation. So yeah, this thing could use a little bit of help in order to, put out a bit more RF power and achieve some modulation there. I have the positive lead of my voltmeter attached to that exposed jumper on the rear of the Globe Scout transmitter, and I have the negative lead of my voltmeter attached directly to the chassis. So any guesses as to what the high voltage level is going to be on that jack? I'll flip the switch to transmit and let's take a look. Over 400 volts is present on that exposed lead. And that 400 volts is present all over the inside of this transmitter. So I'll just flip this back into standby. So extreme caution needs to be taken whenever you work on a transmitter like this. You never ever want to come across that high voltage. So there's a lot of modifications that we can do to really increase the performance of this transmitter. So if you're interested in seeing a modification video on this Globe Scout transmitter, let me know in the comments below and we'll revisit this in the future and we'll hot rod the Globe Scout. Thanks for stopping by the lab today. Hope you enjoyed this video involving this Globe Scout transmitter. If you did enjoy the video, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos coming like this in the near future. So I've got a lot of very interesting antique and modern electronic devices to share with you guys. Lots of very interesting repairs and restorations planned for the bench. So if you haven't subscribed, you might want to do that right now as well. In the previous video, I posed the question, would you like to see me depot the main power transformer out of that previous video? And that previous video involved a neat little tool from the late 30s. The answer to that was an overwhelming yes. So we are going to depot that transformer together. Right now I'm busy designing, I guess I could say, a tool to make that a little bit easier. So when we depot that transformer, basically what we're doing is we're melting the tar inside that transformer and we're going to pull the insides out of the transformer and see what they've hidden inside there. So it should be a very interesting little process that we're going to do together. So thank you for your comments and suggestions in that video. If you're interested in taking your electronics knowledge to the next level, and if you're interested in learning electronics in a very different and effective way, you might want to check out my ongoing electronics course on Patreon. I'll have the link just below this video in the description, and I'll also pin the link at the top of the comments section as well. So, until next time, take care. Bye for now.